Bill here, Oxford College Physics. Let's do some dispersion with triangular prisms, shall we? So we'll look at it in general, and then we can do a little problem after that. But ultimately, what we want to do is take some triangular prism. So dispersion with a triangular prism. So we can take ourselves some nice prism here. Has some apex angle, let's just call it A. Go ahead and put its base down here like that. And what we're going to do is we take some white light and we shine it on this. So I got this little band of white light. Already looks like a bad spot. This striking here, we got the normal to that surface boundary right there. And take some white light, comes in at some angle of incidence, theta 1, and then what does it do as it enters the prism? It undergoes some dispersion, some angular separation. So, just look at the two paths. We'll take the red end and the violet end, and we note that in general, again, the index of refraction for the violet end is going to be greater than the index of refraction for the red end. So let's just trace out this violet path here. So we'll say that the violet comes down something like this, bending towards the normal. It's going to strike that location, and that's great. And then what is it going to do? Well, there's a normal with respect to this position as well. And what do we get? Well, now it's going to bend outward, away from the normal as it exits the prism. And get some amount of bending going on. There we go. It goes like this. So there's the violet. We've also got the red to deal with. Let's see what the red's going to do. Well, the red is going to undergo some refraction as well, bending towards the normal, but not as much as the violet does. So put it a little bit different angle here. So there it is. Notice there's some angular separation between the red end and the violet end. Great. Throw in a normal over here. And what does it do? It bends outward. Well, but it's not striking this at the same angle that it's leaving here, because these two surfaces are not parallel to one another. What's going to end up happening, well, yeah, it bends away from the normal, back out into air, but it doesn't bend as much as the violet. And we get that these two ends continue to diverge from one another. So what we have is we've got a couple different dispersions taking place. We've got the dispersion inside the prism, and then we have a continued dispersion angle outside of the prism that is non-zero, like in the case that we had with the parallel surfaces. So what we want to be able to do is figure out what is this dispersion angle here. So let's name a couple things. Use red and violet, that will be helpful. So we've got a theta 1 here, entrance angle. We've got this, we can call this for violet, theta 2 violet. Then we've got this angle here, we can call that theta 3 violet. And then we've got this angle here, we can call theta 4 violet. All right, we've got these nice thetas there. If we can figure out what theta 4 violet is, well, we can do the same thing for theta 4 red and look at the difference between them to figure out what that is. So we can draw those in. Why not? Let's just do it. We've got ourselves this. That's going to be a theta 2 red. We've got this. That's going to be a theta 3 red. And then we've got this. There's a theta 4 red. We can name some dispersion angles here. We've got the dispersion inside the prism. Let's call that delta 1. And we've got the dispersion outside of the prism. We can call that delta 2. And what do we know? Well, delta 1 is just going to be the difference of those two angles. We've got theta 2 red minus theta 2 violet. And then we've got this dispersion angle here. The normals are oriented in the same way because it's the same surface. We've got a theta 4 violet minus theta 4 red. I know that theta 4 violet is going to be the bigger one because it's bent away more from the normal. So I want the dispersion angle to be a positive angle. So I'll say theta 4 violet minus theta 4 red. Do it the other way, you get a negative angle. Just take the absolute value. That's fine too, but ultimately this angle has to be bigger than that one. So we'll just go ahead and define that. So the trick is, if we can figure out what the theta 4s are. So we got this surface boundary over here. We've got, say, we've got an N1. We say N1 is the index of refraction of air out here. And then we've got, within this prism, we've got some N sub violet and N sub red. So we're going to go from air into the prism, this entrance boundary here, and we've got, just in general, N1 times the sine of a theta 1 is equal to N sub, I'm going to put RV for either red or violet, times the sine of theta 2 RV. So we're using red, we're getting the red angle, we're using violet, we're getting the violet angle. That's great. So we've got that going on for us. It's all kind of scrunched in there. It's a white light. So that's good. And then we've got this exit boundary over here. We're going from the prism at these angles, theta 3, into air, where we've got the theta 4s. We're going from these indices of refraction in the prism back out into air. So we've got ourselves N3, sorry, not N3, N red or violet times the sine of theta 3 red or violet is equal to N sub 1 times the sine of theta 4 red or violet. Recall, the index of refraction for air is the same for all the colors, so we just say, hey, that's just going to be unity 1. Just call it N1 for air. And this is what we've got. So we've got the refraction for the entrance boundary, and then refraction at the exit boundary. So what we need is the bridge in between these. Getting this is easy. If we know the entrance angle and we know the indices of refraction, we just go ahead and figure out what theta 2 is for the red and for the violet. Great. Then we come over here and say, well, if we know what theta 3 is, we can get theta 4. That's easy. We need to be able to get from theta 2 to theta 3 though. So we need to get theta 3 red violet from theta 2 red or violet. So let's do this. Let us just look at one of the paths and see if we can make some angular association between things. So we can take this prism here, we've got this apex angle A here, got a little crooked, fix that up. And, excuse me, I'm just gonna draw one path because it doesn't really matter. We can take some entrance angle. We had our theta 1. We've got some angle of refraction that takes place. We've got some theta 2 there. We've got the normal for this boundary here, which gives us a theta 3 there. And then we've got some further refraction that takes place. Messy. Make it a little bit bigger than that. Well, looks like I almost did the same thing. That's okay. We've got some theta 4 there. So this could be for red or violet, doesn't really matter. We just want to be able to make some angles here. So how do we get from theta 2 to theta 3? We build up some triangles here, right? So we've got this apex angle here, angle A, a little bit more concise there. I could call this some angle B. I could call this some angle C. And then we can note that we've also got some right angles in here. There's a right angle, here's the normal, right there. There's a right angle right there. There's the normal, there's the surface regarding that normal, and that's good. So we start off with this. We've got this triangle, ABC. A plus B plus C in terms of angles have to be equal to 180 degrees. A plus B plus C is equal to 180 degrees. And then we can go look at how B is related to theta 2 and how C is related to theta 3. We have to have that B plus theta 2 is equal to 90 degrees. That 90 degree angle entails both of those. So we've got B plus theta 2 is equal to 90 degrees, which we can write as B is then equal to 90 degrees minus theta 2. We'll come over here and say, well, this 90 degrees has to be theta 3 plus C. So C plus theta 3 also has to be equal to 90 degrees, which allows us to say that C is equal to 90 degrees minus theta 3. So what can we do then? Well, we can take these two quantities and substitute them in there, what we have for B and C. So we can write this then as A plus 90 degrees minus theta 2 plus C, which is 90 degrees minus theta 3, is equal to 180 degrees. All right, so we've got a 90 plus a 90. Hey, that's 180. That's going to cancel out this 180, which just leaves us with A minus theta 2 minus theta 3 is equal to a 0, or theta 3 is equal to A minus theta 2. That's important because that is the bridge between the entrance boundary to the exit boundary. Once we get what theta 2 is, which is really easy, we can go ahead and figure out what theta 3 is based upon the apex angle, and then go ahead and get theta 4 utilizing Snell's law. So that's exactly what we're going to do here. And do a little problem. All right, let's do a problem. Here it is. All right, so here's our problem. We've got ourselves a prism with an apex angle of 60 degrees. So we have some white light entering that prism at an angle of 40 degrees with respect to the normal of the interface boundary at the entrance. And we've got dispersion angle within the prism, the angular separation between the red and the violet end. And we've got the dispersion angle outside of the prism upon exiting. Again, the angular separation between the red end and the violet end. Let's just go ahead and say that the index of refraction for the red end is 1.48, and the index of refraction for the violet end is 1.51 inside the prism. And we'll say that outside we are in air, N1 is equal to 1.00. So, this is what we've got going on. We just go ahead and start figuring things out step by step. So we look at this entrance boundary. And we have theta 2s, right? We've got a theta 2 for violet and a theta 2 for red. Kind of small, but got this. Theta 2 red. And we've got this. Theta 2 violet. And we've got, for part A, that dispersion angle delta 1 is going to be equal to theta 2 red minus theta 2 violet. So we go ahead and we'll look at some Snell's law, where we've got N1 times the sine of a theta 1 is equal to N sub red times the sine of theta 2 red for the red end. And then for the violet end, we have N1 times the sine of theta 1 is equal to N violet times the sine of theta 2 violet. Violet. All right, so what do we want to do? We want to solve this for theta 2 red and theta 2 violet. Dividing both sides by the index of refraction, taking the arc sine of both sides, we've got for the red end, that theta 2 red is going to be equal to the arc sine of N1 over N sub red times the sine of a theta 1, which gives us that theta 2 red is going to be equal to the arc sine of 1 over 1.48 times the sine of, let's say, 40 degrees entrance angle. Yeah, 40 degrees. We can compute that really quick, right? Let's just do that. We've got arc sine 1 divided by 1.48 times the sine of a 40 degrees. We get 25.741. 25.7148 degrees is the angle with respect to the normal interface boundary for the red end. And then for the violet end, we've got something really similar. Theta 2 violet is equal to the arc sine of N1 over N violet times the sine of a theta 1, giving us that theta 2 violet is equal to the arc sine of 1 divided by 1.51 times the sine of 40 degrees, which gives us, oops, 1.51, 25.1942. 25.1942 degrees. So overall, we look at this angular separation, the dispersion angle between the red and the violet ends, and we've got theta 2 red minus theta 2 violet, which is then going to be the 25.7148 minus 25.1942. 25.7148 gives us 0.5206. 0.5206 degrees. A little bit over half of a degree. That's not that big of an angular separation, but some angular separation nonetheless. So, that's it. There's part A. What we really in the end want to be figuring out is what is this dispersion angle, the exit dispersion angle. So, go on and proceed. So, now we've got part B. Well, let's grind some little things here, just keep things straight. We've got this angle, theta 4 violet. Got this angle, theta 4 red. And we've also got this angle, theta 3 red, and this angle, theta 3 violet, relative to the normals where they are striking. And dispersion angle, delta 2, is what we want to ultimately figure out. Delta 2 is going to be equal to theta 4 violet, the larger angle, minus theta 4 red, the smaller angle. That's great. Then it's a matter of getting these angles. Well, we're going from the prism back out into air. So we have, for the red, N sub red times the sine of a theta 3 red is equal to N1, going back out into air, times the sine of theta 4 red. And for the violet, got something similar. N sub violet times the sine of a theta 3 violet is equal to N1 times the sine of theta 4 violet. So we can go ahead, take these, solve them out for theta 4s, right? So for this one, we get ourselves theta 4 red is then equal to the arc sine of N red over N1 times the sine of theta 3 red. And for the violet, theta 4 violet is equal to the arc sine of N violet over N1 times the sine of a theta 4 violet. Excuse me, 3 violet. These are 3 violet. So what do we need? We need the theta 3 violets, right? And as was demonstrated just prior to this, we've got that theta 3 is equal to A minus theta 2. There's a rotation. Rotation between theta 2 and theta 3. It's equivalent to the apex angle. That's it. So we have that theta 3 red is equal to theta 3 violet is equal to, well, 60 minus theta 2 red, and 60 minus theta 2 violet. I'm messing something up really quick here. That minus theta 2 red, 25.7148. 34.2852. And theta 3 violet, 60 minus theta 2 violet, which was 25.1942. 34.8058. Notice they do not strike at the same angle. They strike at different angles. That's because there's a disorientation between the two surfaces. They're not parallel to each other. So we've got our theta 3s now. We can go ahead and start sticking those in there. We've got theta 3 red, theta 3 violet. We know what n red is, we know what n violet is. Let's just evaluate these. Sticking that stuff in, and we've got 1.48 times the sine, 34.2852. 4.2852. Arc sine of all of that gives us 56.4810. 56.4810 degrees. There's the exit angle for the red end. And then we've got ourselves the arc sine, 1.51 times the sine of theta 3 violet, which is 34.8058. And we've got ourselves 59.5309. Those are quite different. What do we have in the end? Delta 2 being theta 4 violet minus theta 4 red is then this minus this. So we'll just do that. Minus 56.48. We get ourselves 3.050. 3.050 degrees. Which is pretty large compared to delta 1, is it not? It's 6 times as big as that almost. That's a big dispersion angle. Now what do we have? We have the entire rainbow in this little spot right here. It's a pretty small angle still, 3 degrees, but as we get further and further away, that rainbow is contained within a larger and larger space. And eventually, it comes on the ground or hits some screen, and we got ourselves the rainbow. Thank you, Prism. And thank you. Have a good one.